Hi, my name is Michelle Chong, and this is a recording made for the 2022 IEEE Conference on Decision and Control for my paper entitled Entropy for Incremental Stability of Nonlinear Systems Under Disturbances. Before I get started with my recording, I'd like to apologize for any coughs or raspy voice that might occur during this recording, as I'm recovering from a nasty bout of COVID. In this paper, we consider a forward-complete nonlinear system, where the initial conditions belong to a known compact set K, with inputs D being measurable, locally essentially bounded functions of time to the set D that is closed. Pictorially, we see that given two trajectories of the system initialized at two different inputs and two different initial conditions, we say that the system is incrementally stable if the two trajectories converge to each other over time, or asymptotically. To be more precise, we say that the system is beta k incrementally stable, whereby beta is a class KL function if for any two inputs and any two initial conditions, the trajectories of the system converges to each other asymptotically, which is captured by this beta, which is a class KL function right here. Similarly, we can also define what we call practical incremental stability. Namely, we'll like the solutions to not just, not necessarily converge to each other, but to converge to within an epsilon neighborhood of each other. To be more precise, we say that a system is beta k epsilon practically incrementally stable for a margin epsilon that is positive if for any two inputs and any two initial conditions, the trajectories converge up to a margin of epsilon within this epsilon margin of each other, asymptotically. Building towards entropy, we first define the data rate, which is a number of samples of the state space constrained to the set K per unit time for either of the incremental stability properties we mentioned earlier. Roughly speaking, entropy is then the asymptotic data rate, which is done by taking time to infinity, and this captures the growth rate of the data rate. Our objective is to provide bounds on the entropy for a class of system that is forward complete with inputs to achieve incremental stability properties. We'll take the approach of Bowen and Dinnerberg, whereby they have done so by constructing what they call spanning sets. In our work, we're going to call these sets approximating sets for reasons that will become clearer later. Another work that is highly related to this approach we've taken in this paper is by Liberzon and Mitra, where they studied autonomous systems without inputs and were after exponential incremental stability properties. In our work, we consider a general class of nonlinear systems with inputs, and we consider more general incremental stability properties. First, let us examine what we mean by an approximating set. An approximating set is a collection of points in the set K, which we can see here, whereby there must exist at least one point in this approximating set such that the system satisfies certain incremental stability properties. We call this particular set T beta K M epsilon asymptotically approximating if at least one of these points will result in a trajectory initialized at that point to be close to the trajectory of the system for a particular initial condition in the known compact set K that is also incrementally stable, which we show here. Note the existence of the M epsilon, which has appeared in the first argument of the class KL function. And that is a result of what we need to construct these approximating sets. This consequence was also observed in the paper by Colonius and Hamzi that also constructed approximating sets, whereby they've done so for achieving practical stabilization. We also have the similar definition for the practical incremental stability counterpart, and note the presence of m epsilon in both its first argument as well as the margin, as we would expect it. We're now ready to define what we mean by estimation entropy. Let SA be the minimum cardinality of the T beta K m epsilon asymptotically approximating set. Since SA is the minimum number of functions needed to approximate the state X with the desired accuracy and convergence rate, the estimation entropy, which we have defined both for incremental stability as well as practical incremental stability, is the average number of the state estimates over the time interval 0 to t. The inner limb swoop captures the growth rate of the minimum cardinality, and by taking this limit as epsilon goes to 0, we obtain the worst case over all epsilons. The same argument can be made for the epsilon practical estimation entropy. Now we proceed by finding upper bounds and lower bounds for the estimation entropy. To obtain an upper bound on the estimation entropy, as mentioned earlier, we'll do so by constructing the approximating set, given that the system is incrementally or practically incrementally stable. This approximating set forms a delta cover of the set K, where delta is what we call the resolution. Pictorially, it means that we cover the compact set K with balls of radius delta. And finally, using the Minkowski-Bolajon dimension, or otherwise known as upper box dimension, whereby we see that for any bounded set K of dimension n, Rn, we can upper bound this quantity by its dimension n. And it is through this relation that we were able to establish the upper bound on the entropy, on the estimation entropies. As we can see, the construction of the approximating set is crucial in obtaining these bounds. In this table, I've summarized the various incremental stability properties that we're studying in this paper and a resolution of the corresponding approximating set. In lemma 1, we showed that if the system is beta k epsilon practically incrementally stable, then there exists a finite t beta k 2 epsilon practically approximating set, with the resolution given by this quantity in the last column. The resolution is a function of the time interval t and the practical margin epsilon and the matrix measure of the Jacobian of the system, and actually the upper bound of this matrix measure, mu bar. Note that this matrix measure can be both positive and negative. In lemma 3, we consider a system that is beta k incrementally stable, and this results in the construction of a t beta k epsilon practically approximating set. From lemmas 1 and 3, we see that sampling the state space results in a decrease in the approximation accuracy over a finite time interval. So by considering a system that is practically incrementally stable, epsilon practically incrementally stable, we obtain an approximating set that is 2 epsilon practically approximating. And in the case where we considered the system that is incrementally stable, we end up with an epsilon practically approximating set. In lemmas 2 and 4, we obtain the exponential counterparts, which results in sharper bounds in the resolution. Now on to establishing the lower bound on the estimation entropies. Here we'll use a volume growth argument that I'll explain in the next couple of minutes. First, consider the reachability tube of the system over the interval 0 to t with initial condition in compact set K and input in D. We then cover the reachability tube with balls centered at a trajectory with initial conditions initialized at the approximating set with radius delta. The construction of the radius delta and its exact details can be found in the paper. Now with this, we can see that the minimal cardinality of the approximating set can be lower bounded by the volume of the reachability tube divided by the volume of each of these balls. And it is through this that we are able to establish a lower bound on the estimation entropies. A very nice byproduct through the construction of all these approximating sets is that it induces a state estimation algorithm with quantized and time-sampled measurements. Here, our standing assumption is that the system we're considering is alpha k epsilon practically exponentially incrementally stable. And here, our system has outputs a measurement that goes to the encoder. The encoder can only transmit a quantized version of its states at a particular point in time. On the receiver side, we have a decoder which outputs the estimate. However, this decoder only receives the quantized state measurement and does not have access to the input D. Now the question is, how do we generate the quantized measurement x star of k at each transmission time? Firstly, note that we are given this compact set k at the initialization. We then construct our approximating sets as follows. And notice that since we measure our system at a particular point in time, so say at the transmission time, which is depicted by this orange dot right here. We then choose the point that is closest to this measurement and transmit it as our quantized state measurement. At the decoder side, it receives the state estimate and outputs a state estimate that is initialized at the received quantized state measurement and with zero input, since it doesn't have access to the input on the receiver side. Now, at the next iteration, we're going to generate a new K set, which we denote K1. This set will be centered at the last transmitted quantized state, denoted in green, with a radius that has been shrunk in the following manner. Note that alpha is a property of this, is a stability property of the system concerned. Again, we then generate the approximating set. Notice where the measurement falls and choose the quantized state measurement to be transmitted to be the one that's closest to the measurement, and then generate a new K2 with a new radius delta 2. With this iterative procedure, whereby we have chosen our estimate to be the trajectory of the system initialized at the last quantized state that is received with zero inputs, since it's not accessible on the receiver side, we can guarantee that if the system has a bounded matrix measure of its Jacobian in X, and is alpha k epsilon practically exponentially incrementally stable, then for all of these time intervals, we can guarantee that the state trajectory, the true state trajectory, is always within this k set that we're constructing at each iteration. We can also guarantee that our state estimation error, depicted in items 2 and 3, are always bounded. And actually, within the time interval in which we are between transmissions, we can guarantee that the state estimation error can be upper bounded by an exponential term, decaying exponential term, plus some term that is a function of the epsilon practical margin. Here we observe that if our system is exponentially incrementally stable, namely epsilon is equal to 0, then we recover an exponentially decaying estimation error over time, which is the result that was covered in the paper by Liberzond and Mitra. To conclude, we have introduced notions of estimation entropy for incremental stability and practical incremental stability of deterministic nonlinear systems with inputs. We have provided bounds on these estimation entropy via the construction of approximating sets. The construction of the approximating set inspired a robust state estimation algorithm for quantized and time-sampled measurements. In the future, we intend to demonstrate the generality of this framework to new and exciting application areas, including the resolution of encrypted control, and also for the formal verification of dynamical systems. With that, I thank you for your attention.